and B for the wonderful weather. So I managed to whittle my talk down from 5 hours to about 3, so I thought we've got plenty of time this afternoon to... No, I'll fit it into an hour. All right, so let me just recall a couple of things, mainly from Clement's talk. So, in a various order, this is not in time order. Actually, Mark Levine came first, made some observation, but when Vojevodsky did his work, it provided everything one needed for the construction of a Tannakian category of mixed-state motives. So the whole motivic story, the basic part, has already been established. That was for number fields, I should say. Yeah. All right, so it says if F is a number field, have Tannakian category that call it MTF of mixed-state motives over, and I'm going to say, actually I'm going to change this to OKS over unramified, so it's over OKS. That means motives that are over the ring of integers that are unramified away from S, whatever that means.
K is F?
Sorry?
K is F.
Oh, yeah, I'm trying not to use K there, but okay. All right, and so the basic fact is, so you could make up any Tannakian category, but it has to be compatible with K-theory, so such that X1 in this category, mixed-state OKS, OF, you can make the substitution of Q by Qn, so the simple objects in this category are these Qn. If I write Q, it means Q of 0.
Sorry, maybe you said that. I'm still confused on what's conjectural and what's established.
So this is established.
This is established.
So what's conjectured is that there is a Q-linear Tannakian category of mixed motives, and its X groups give you K-theory and other things, right? And so the big obstruction to doing that, given Vojevodsky's work, is the solution, is the proof of the Beilinson-Soulé vanishing. And that can be phrased here as saying, whatever you've got here, it's just saying this guy vanishes whenever n is equal to or less than 0, except, well, if I put a dot there, right? So the X groups in this category should vanish when n is equal to or less than 0. And the whole point is this has weight 0, that has weight minus 2n, and things in motivic land have a weight filtration, and so the weight filtration is increasing, and that tells you you can't extend things of low weight by something of high weight. Right, so this is saying you can only extend Q by something of smaller weight. That's the whole point of Beilinson-Soulé. It says you can't do things backwards. And that is a problem, could be a problem in group homology. And I think it's sufficient to just prove it for fields. Right? So that's the big obstruction to progress. But we can work with mixed-state motives.
Okay, so isn't Beilinson-Soulé about vanishing of negative X groups? Rather than
no, but it's also telling you you can't extend by things of Q by something of larger weight, or even equal weight, except for X0.
Okay.
Let's not worry about it. I mean,
what's the statement? Sorry, such that.
Sorry?
Such that.
Yeah. Yeah, I should keep going, otherwise we you won't enjoy your hike. So it's equal to Q, sorry, sorry, where am I? This is, I've lost track of where I am. It's 2n minus 1 fq, right? And this is for n bigger than 0, and x0 mt q of 0 is equal to q. That's just k0 of the field line. And all the other ones vanish.
This is for n bigger than 1, and for q of 1, there's a, it depends on s, right?
Sorry? Yeah, sorry, I should. Happy now? Yeah, sorry about this. So, Tannakian categories are categories of representations of some affine group scheme, so, or a pro-algebraic group, if you like, an inverse limit of. So I didn't understand the terminology first. An affine group is algebraic if its coordinate ring is finitely generated. Right, so, all right. So the fundamental group of this category, that's of MTOKS. So I'll call it K. Sorry. So, well, it's an extension, so there'll be pi 1 of this category. So the category is going to be represent. I should have just made it K. And it maps to GM. So the representations of GM are just the QNs, right? So representations of GM, that's the multiplicative group. It's just, they're all powers of the one basic representation. There's a kernel here. I'll call it K. I think this is why I didn't want to call it. Right. So it turns out here you can largely ignore this. This is just telling you weights. And for the experts, I'll take the base. All right. So this guy here is pro-unipotent. It's a group. It's an inverse limit of unipotent groups. And so it's Lie algebra. So the Lie algebra, maybe I'll call K Fs. So it's free. That's basically because all the only x you get are x1s. All the higher x vanish, so that forces, so no relations. And well, I could write down it's H1, but I won't. But I'll do an example in a second. So, yeah. So example, let's take OKS just to be Z. And in this case, K, when I don't put anything on K, I'll mean this example here. It's a free Lie algebra on these generators, sigma 3, sigma 5, sigma 7, and so on. Maybe I put sigma 9. All these are generators, and this guy has weight -6. So this corresponds to a copy of Q of 3, so it has weight -6. This has weight -10, so that's Q of 5, and so on, right? And I'll explain the role of these guys later. Technically, I should complete it, but this group, if I take the de Rham fiber functor, this has a canonical splitting. And so that grades this guy over here. So this Lie algebra is really the degree completion of this thing. So I'm going to be sloppy, slightly. I mean, it's not. Everybody is slightly sloppy here. Right, so now, well, if I try to dot every I and every T, it'll take 5 hours. All right. So I want to talk about depth filtrations. So, yeah, so representations of this Lie algebra, graded representations of this Lie algebra are mixed Tate motives. Right, so it's absolutely beautiful. So let's talk about depth. So I'm going to talk about depth filtration in a very different way, but it's equivalent. And I'm more of a topologist, so I work with the covariant objects like this guy rather than with multi-zetas like Herbert. All right, so let's... Right, so I'm going to restrict the fields I work with, and I'm going to set ON equal to Z adjoined, these are the nth roots of unity, and I'm going to invert N. You have to do this, just otherwise if you reduce mod P for any P dividing N, then this behaves badly, right? So, so this is going to be our OKS. So it's basically the integers in a single-atomic field. Right, so this is just contained in Q UN. So if I take n bigger than 2, all the k even and positive of Q is equal to 0, and all k odd have rank R2, which is equal to phi n over 2. Right? So it's the number of complex conjugate pairs of embeddings of this field into the complex numbers. And I'll set Kn is just equal to K of this, whatever it is, K, Q, N, whatever. So it's just...
You mean 5n over 2 here?
Sorry?
5n over 2.
Yeah, sorry. I'm doing a bad job here. Okay, so now... Right, so there's a depth filtration, and I will define it. So you start out with Kn, and it's going to be D0, and then you're going to have a D1 and a D2, and so on. And so how do we define this? And I'll just set up the notation, GR D dot of K in is just the direct sum of the dj mod dj. And you also will have that dj bracket dk is contained in dj plus k. So you've got a filtered Lie algebra. So what I'm going to do now is I'm going to set un to be equal to gm minus mu n. So what is this? So if I over c, this is the gm. So if you like, unc is just the c points of gm, which is just the non-zero complex numbers minus the nth root of unity. So if you like, this is P1 minus 0, infinity, union mu n. And so this is somehow a basic object when you want to study mixed-tape motives over, say, this field. So example, mu1, which u1 is just p1 minus 0 and an infinity, which plays a major role in this theory. And all right, so I have to digress here. I'm going to define unipotent completion, and I would hate to contradict Clement, who said you can't write down Tannakian fundamental groups. I'm going to do it. So I want to talk about unipotent completion. And so this is well understood in various contexts and so on. But I want to be very clear. It's also called Maltsev completion. It used to be. It's maybe not exactly the same thing, but it is in all the cases we're talking about. So I'm going to take a discrete group. And to make things simple, I will assume that H1 gamma Q is finite dimensional. These two diverge if this is not finite dimensional. And so I'm going to put U rep gamma is just equal to the unipotent, the category of unipotent representations of gamma over Q. Right? It's Tannakian. Tannakian, a category is Tannakian if it looks like the category of representations of a group. You know, it has, if you axiomatize it, you've got to be very careful how you do it. You know, I recommend Deligne Milne if you want to learn this stuff. I resisted learning Tanaka theory for decades, and when I finally did, I realized I could have simplified a lot of papers that I wrote. I mean, it allows you to see some things very clearly. But anyway, it doesn't help that much here. But so it's Tannakian. So pi 1, it does in other situations, like in pi 1 of this category, and the fiber functor is just take the underlying vector space, whatever it is. This is gamma unipotent over Q. So it's a pro-unipotent group. So that means inverse limit of unipotent group. So I can see you don't like this, so I'll give you a very concrete description. I'll give you two. And I each take one line. One is you can take, so let's take, what's the name of a field? I'm going to call it K. So what's gamma unipotent K, the K points of this guy here? So it equals the group-like elements of, you take the group algebra of gamma and you complete it in the iadic topology. What's that? That's just the inverse limit of K gamma modulo powers of the augmentation ideal, M. So that is a Hopf algebra. When you complete it, it's a complete Hopf algebra, and you take the group-like elements, the elements that satisfy delta x equal to x tends to x. That's it. They're the K points. Quellen has an appendix to his rational homotopy paper, which is a really good reference for this. Okay, it's appendix B, I think. So that's that. Or if you want the coordinate ring of gamma unipotent, it's just equal to the direct limit of hom Q gamma mod I to the M into Q. So there, it's explicit. And I'll do one example. Suppose gamma is a free group on, say, S1, Sn. So you can, by the way, there's going to be a map from gamma into gamma unipotent, the Q points of this group. So what, it's just going to be gamma unipotent is equal to x of the freely algebra on big S1, big Sn completed, which is contained inside Q S1. That means non-commutative Tau series. So the group-like elements of this are just the exponentials of the Lie words. And then what's the map of gamma in here? Just gamma maps into the Q points. You just take gamma, yeah, so you just take Sj goes to exp of Sj. So it's very concrete. So that, sorry, Clement.
It's better, right?
All right, so that's, why am I spending so much time on that? Because we're going to, so we have to use the right base points, but Deligne-Goncharov did a lot more than this, but if you look at, say, yeah. So I'm going to, I'll also, let me just say it this way at first. O of pi 1 of un, and I'm going to take a specific base point, which I'll describe. I've got to use tangential base points here. It is an ind object of MTON. So the coordinate ring of this, and it's the same as saying the Lie algebra of, whoops, I didn't put, of pi 1 unipotent of un v, which I still need to tell you about, is a pro. I'm going to drop the ind in the pro. It's harmless, right? And so that means, for example, so both have action of Kn. I mean, that's what, if you have a mixtate motive, pi 1 of mixtate motives acts on it. So, so we want to use this to define the depth filtration here. So I've got to define the depth filtration on this guy. And I'm going to induce it on this. So, and it's going to look very different from the multi-zeta way of thinking about depth, but it's the same. So, what you can do with UN, I need to tell you what the base point is. So here is C. I mean, this works over OK, whatever. So here's 0. Here are our roots of unity. And here's 1. And I'm going to choose this tangent vector here. So what is it? I'm going to take V equals d dx, where x is the coordinate here. And it's going to be an element of the tangent space of 1 of P1. And the reason you choose this one, you need to choose something that has non-zero reduction mod P for all P. Or anyway, all the P that don't divide in. All right? So that's that. And and what does pi 1 here mean? It means you leave here with that velocity vector and you return here. And if you don't like tangent vectors, just take the real oriented blow up. That will replace this point by a circle, and that tangent vector would become a point on it, and then this would be a surface with boundary. Okay? So, all right, so let's define the depth filtration here. So we have an inclusion of UN into GM. And in fact, and what's pi 1 unipotent of GM? Well, this is just, of course, it's just cyclic. So it's going to be, it's isomorphic to Q times something I'll call E0. I'm going to have another E in a minute, it'll become clear. You think of E0 is the log of the circle around 0. Log of this guy. All right, so then you get a map, and I'm going to denote this guy up here. I'll call this guy Pn. So I get sick of writing So this gives me a map from Pn into another wrinkle is we know it's really it's a graded representation of this. So the G, it's probably erased now, in the pi1 of mixed-state motives actually canonically grades the de Rham version of this. All right, so now, into the Freely algebra on E0, which is just Q0, right? And it has a kernel. This is just the kernel. And now, the depth filtration is D0 of Pn equals Pn. D1 of Pn is equal to the kernel of this map. And D2, Dm of P, or maybe I should call it dd of Pn, is just equal to the dth term of the lower central series of A. A is free because every subalgebra, really algebra is free. And now, I'll show you the n equals 1 case in a bit. So, but let's just stick with this. And now I'm going to define, so we have K, so this puts a filtration d dot on the derivations of Pn. So delta as in dm is equivalent to saying delta of dj of P is contained in dj plus m of P, all j. You only need to check a few j's, like j equals 0, 1, and 2 or something. All right? So now that puts the filtration on this, but now we just restrict it to Kn maps into these derivations on Pn. And now we've got a filtration here, d dot, you just restrict it, you just pull it back to here. And then you just pull back. To here. That's the depth filtration. And let me just do the n equals 1 case quickly. So n equals 1, so u1 is just u equals p1 minus 0 and infinity. And here is 0, is 1. I've got a generator here. I mean, these are the E0 and the E1 are essentially logs of these circles, but they're really the de Rham analog. But anyway, so P is going to be P1 is just the Freely algebra on E0, E1, and completed if we need it. And we have the map from L, so we've got P maps to L, E0, so that's really L, E0, E1 maps to here, and you've got a kernel. So what's the kernel? I'm going to start drawing a picture of this guy. Yeah, I mean, there are 100 ways to work it out. There are a lot of group theories here. So you'll see that this is actually the Freely algebra on all the e to the j, E0 to the j, E1. So, and what does this mean? U dot V is add U on V, so that's just U bracket V, right? That's the notation. So this would just be, for example, E squared E0 squared E1 is just E0, E1, right? And so the kernel is freely generated by these guys. And so now I'll draw a picture. So another thing is these guys have weight minus 2. That's these guys span copies of Q of 1. So H1 of E1 minus 0, 1, and infinity, it's equal to QE0 plus QE1, and it's also isomorphic to Q of 1 squared. Right? We've got to keep track of these things. One way to say it is that tells you the way the Galois group acts on it, or you use Deline's theory of mixed height structure or whatever. But these are classic thingos of E1. So you can see already this guy will have weight, this guy has weight minus 2j minus 2. The weights behave very well, as you would, in the way you would expect. All right, so now, so let me draw you a picture here. So this will be weight, and this will be depth. And so we have weight minus 2. We only have even weights minus 4, minus 6, minus 8, minus 10. That's probably enough. Depth, we have depth 0, 1, 2, 3, and so on. So here we have E0s. The only thing, I mean, it's a filtration. And I'm sort of, anything below here is in depth 0, anything below here is in depth 1. So E1 has weight 1. But then you also have E0, E1 here. You have E0 squared, E1 here, E0 cubed, E1, E0 to the 4th. All right. Now, so let's look at this a little bit. This is going to be a Q of 1. This is a Q of 2. This is a Q of 3. A Q of 4. And a Q of 5. That's a Q of 5, weight minus 10. And now where could we get extensions? So the you can only get, these are the only possible extensions, Q of these guys here, where this is, did I do that right? Ah, no, sorry. I have to go one for. All right, so there's a Q of 6. So, I put those. So the only possible extensions we can get are this one and this one, and there'll be a lot more. And this one is an extension of Q of minus 1, sorry, Q of 1 by Q of 4. This one has period zeta of 3. And this is well known, and this one has period zeta of 5. If I quotient out the whole picture under this line, I'll draw a yellow line. If I take the quotient by D2, this thing, if you move it around, if you move the base point, this is the so-called polylogarithm. So this is the polylog quotient, which is much studied. This is the first thing that was studied. You write down, you can vary the base point here, and you get the so-called polylogarithm variation. This is the fiber over this tangential vector, and it's the one, well known, all these periods were computed, and this is telling you that sigma 3 takes this generator to that. You've got this extension corresponding to zeta 3. This extension here is given by the action of zeta 5. So what this is telling you is that this is telling you that, yeah. So depth is going to be basically degree in E1. Here you get, it's free, so you take brackets of these and so on. So this is telling you that each sigma 2j plus 1 in K is in depth 1K. It's not in, it's not equal to 0 in GR depth 1 of K, right? So we know all the sigmas have depth 1, and they're linearly independent. It's a good thing we have the whole afternoon, because even though I thought this was only an hour and a half talk, it's going slow. All right, I'd like to get up to modular forms, but all right. So you know something. We've been able to understand the depth of the generators of the motivically algebra spec Z. So so here's a question, and I don't know why people started asking this question, but they did, and it is GRD dot of K n free. And I'm going to present results in an ahistorical order because it makes more sense to me. So, I must have lost a page. So, well, anyway. So the first thing is, so n equals 1, and I'm going to talk about this in a bit. 1999, Ihara to Cow. Is that not true. There are depth 2 relations. And they somehow correspond to cusp forms. And that's what I want to talk about later on. So, that's 1. So Deline in 2000, take my years with a grain of salt. Sometimes the date of the publication, sometimes it's the date of the archive preprint. But for n, this is a bizarre one. 2, 3, 4, 8, GRD dot KN is free. And you think, oh, maybe just the first case didn't work. They're free.
6 as well?
Yeah, Herbert here's to make sure I'm honest. Yeah.
Well, if you have 3, then you have 6, I suppose.
Yeah, I left out 6 because I want to make another statement, and the statement, it's slightly wonky. Yeah, there is, okay, you can, is it free at 6? But anyway, I want to point out here the only primes that occur are 2 and 3. And they're also very bad primes for elliptic curves. So, and then Goncharov, and I need a year from Herbert, said n prime, and I think it's greater than 5, is that GRD AN is not free. And I don't think this is very well understood. So I want to make one more remark, is that there is a dual statement for multiple zetas, and I don't usually think in terms of multi-zetas, but let me just mention it. There's a result there, so you know, I've lost a page. There it is, or maybe not. So I can't remember the year, but there's Gangle. I'll state that later. But there's a relation due to Gangle, Kaneko, and Zagier that was proved when sometime about 20 years ago.
When you were 6.
What's that?
When you were 5, when you were 6, or
Okay, but it was proved in ancient history, it's a relation between, a depth to relation between multi-zetas. I'm not going to talk about that too much. Oh yeah, and I should say that the filtration of K is dual to the filtration of motivic multi-zetas. So it's the naive one you define there. Okay, so where were we? Yeah, so I want to talk about Ihara to cow. And maybe I should also put Matsumoto up there. But all right, so I want to talk about period polynomials. So,
before you move on, what's the purpose of this question? What does one learn if it is or is not free?
I mean, depth seems to play a big role in, polylogarithms and all of this. But, I mean, I can tell you why I'm interested, but, yeah, I mean, so for example, if you look at this here, this monomial corresponds to the iterated integral. The integral, it's going to be omega 0, omega 1, omega 0, omega 0, where omega j is equal to dz of a z minus j. So this is the integral that gives you the trilogarithm. This one's related to the integral omega 1 with 3 omega 1s. I mean, there's a lot of structure, there's a lot of stuff going on. So this filtration is related to polylogarithms, and these e's are dual to these differentials. And so when you have expressions, iterated integrals in these forms, they're dual to words that appear in this picture here, right? And so the depth filtration of these integrals corresponds to the depth filtration of these monomials. And so people are trying to understand depth, and you should ask, Radchenko or Herbert Gengel, why they care about depth. But depth reduction was a big thing. I don't claim to say anything about that, but something very motivically very interesting is coming here. For me, the question is, why are elliptic modular forms or cusp forms wreaking havoc with mixed state motives? I mean, they're somehow exerting some control, right? And that's the one idea I want to explain. Because all the proofs of this before is basically Matsumoto, myself, and Francis Brown were just combinatorial. But there was no geometry or nothing motivic in the proof. There's nothing to suggest why cusp forms were having some control over multiple zetas. Okay, so I don't know, does that answer? So period polynomials. So yeah, so I want to look at SL2Z, and I'm not going to get very far into modular forms, and I'm going to take M to be bigger than 0, and I'm going to let H be the defining representation. So I'd like to think of that as H1 of some elliptic curve E. So this is an elliptic curve. So this is the mapping class group. If you like, I would write this as, I'll write it like people here might write it, mod of a torus with respect to a point, right? It's the mapping class group of a genus 1 surface. And so SL2Z acts on this. I'm going to think it in general being a very specific one. It's the quotient of the upper half plane by this one. So this, it'll be this elliptic curve, and this generator will be A, and that generator will be B, and so H is equal to QA plus QB. So, right, so I want to look at H1 of SL2Z with coefficients in S I'll take an even power because the homology with coefficients in an odd power of 0. You can restrict this to H1 of 1Z01 S2MH. And I'm taking M to be positive, so you can see this map is surjective, and this guy here, this is the same as H0, the same group, S2MH, and if you think about it, this is just going to be one-dimensional. Don't worry about what the generator is lately. And then the kernel of this is defined to be the cuspidal homology of SL2Z. So this is a definition. The cuspidal homology is the kernel of this homomorphism. Why is it called that? So this Eichler-Shimura tells you that this thing has a large piece that's given by modular forms. This part corresponds to the Eisenstein series of weight 2m plus 2, and this part corresponds to cusp forms. So this guy here actually has a hot structure. It'll be of type 2m plus 1, 0, plus h 0, 2m plus 1, and this here is the cusp forms of SL2Z of weight. There's many notions of weight here, which is incredibly confusing. So this is the weight as a modular form. This representation has weight 2m, and this hot structure has weight m plus 1. So, but anyway, we've got this guy here. And so let's try to understand something about this class. So every cusp form gives you an element of this group here. And so, but I decided to instead just talk about them as cocycles. So every class in here is represented by a cocycle. So phi takes SL2Z into S2MH. So this is a one cocycle. Sorry, a one cochain. I'll make it a cocycle. All right. So this group, you can write it in several different ways. It's generated by S and T, where S is 0, minus 1, 1, 0, and T is 1, 1, 0, 1. So every cuspidal class is represented. So phi reps, well, phi cuspidal, it says that phi of T is equal to phi of little t equals 0. So that means this cocycle is determined, so phi is determined by phi of S, which is an element of S2MH. So this is just a polynomial. And it satisfies some conditions. The cocycle condition is that, so I'm going to denote it, I'll call this guy R, and it'll be a sort of polynomial in A and B, the basis elements of H1. And so the cocycle condition is 1 minus S times R is equal to, or is it 1 plus S? 1 plus U squared times R equals 0, where U is equal to ST. That's an element of order 6, I think. Yeah, in SL2Z. So anyway, so these are the so-called period relations, cocycle relations. But you have this cocycle. But the important thing is we have this polynomial. So do I only have 10 minutes?
1 minute.
Oh, 1 minute. Okay. So, okay, I'm really going to cut to the chase. So the relations, the Ihara to Cow relations in depth 2 are relations between So they're relations between. So let me just do one example between the sigma, between the sigma j, sigma k in graded depth 2 of k1. And they correspond to these polynomials. So these polynomials, r will equal to r plus plus r minus. So all powers even, meaning even power of a, even power of b, all powers even. And here, the whole polynomial has even degree, but if I have an odd power of a, I have to have all odd. So this is the guy that plays a role, and for every one of these polynomials, you get a set of coefficients, and they give you relations between these guys here. So let me write down, so let me take, so r plus f, where f is the Cusp form, this corresponds to a relation. And let me give you one, delta is equal to the Cusp form of weight 12. So it's equal to something like the product 1 to infinity, 1 minus q to the n to, I think that's right. Is that right?
Times q. Well, no.
And times q.
No, no, no.
24.
Sorry?
24. 24.
The 12 to 24.
Well, I was right the first time.
12 to 24 and times q.
Okay, so anyway, that's what it is. So the even part of the polynomial, I won't write it down. Well, I guess I can. Let me not do that. So it leads you to the relation sigma 3, sigma 9, minus 3 times sigma 5, sigma 7 is congruent to 0 mod d1. And so on. For every other Cusp form, there's a polynomial here whose coefficient of something like x squared or a squared b to the 8th is 1, and whose coefficient of something like a to the 6th, b to the 8th is minus 3, right? So, hey, I'm not.
D3?
Sorry?
Mod D3? Or it's modulo D3? Or what is the...
This is the relation because I looked it up.
Yeah. It's modulo what?
It says D
It's a depth
prime.
filtration. What's the power of D? Power of D in the depth filtration?
No, I'm doing rationally.
But is it modulo D1 really, or modulo D3? Higher depth or lower depth?
Oh, modulo D3.
Right.
Sorry, got it. That's what it said. Yeah. Okay, I have minus 1 minute. Okay, I'll stop. Somebody asked me a question. What's this got to do with? All is to go.
Do you have a theorem?
Well, no, there are many theorems, but the whole point.
We have one theorem.
No, it's, the goal is to explain something that's been explained. I mean, it's all of this stuff is published.
I think the answer.
So I just want to explain one idea, and why. I think this is an important idea, and I'll do it for n. Right. So why do modular
No
form?
ideas, a theorem, a statement. Please.
Why do ideas? Why do elliptic modular forms exert control over mixed-state motives? So maybe I'll just do n equals 1. So you have the universal elliptic curve over M11. That's the quotient of the upper half plane by SL2Z. It sits inside M11 bar, and I'll still denote this by this. So there's one cusp, there's this Q disk. The Q disk, the punctured Q disk is just what we had before, the upper half plane, mod this guy here, 1Z, 0, 1. Now the fiber over this Q disk, over that you have the nodal cubic. So what is the nodal cubic? It is P1, with 0 glued to infinity. Now, nearby, you have nearby elliptic curves, you know, right, like this. And so what you do, and now we're going to remove the identity section. So what have we got here? Here, you get, as a group scheme, when the elliptic curves degenerate to this, they don't see this double point. So what happens if you remove 0 and infinity from here? So this contains GM. And what happens, I could also take level n and I would remove the nth roots of unity. And over some of the cusps, I would be removing the nth roots of unity here. And so what happens when I remove the identity section, I get GM minus 1, which is P1 minus 0, 1, and infinity. If I did it with the other case, I'd get GM minus mu n. And so what's the point I want to make here, I won't be able to say very much, is you use this degeneration of elliptic curves here to see that there's a whole symmetry coming from SL2Z that's acting on the first order smoothing of this guy here over the tangent vector DDQ. And there's a thing called the KZB connection, and it has coefficients that are Eisenstein series, and it's an oracle. It spits out all these complicated combinatorial formulas that I couldn't derive. And it tells you how SL2Z is acting on this. And what happens is sigma 2m plus 1 is congruent to some other derivation of the Freely algebra corresponding to the elliptic curve plus other terms. And these leading coefficients satisfy what are called the Polylogarithms relations. And they're the ones, they satisfy absolute relations. And when you take the same linear combination of these guys, these guys vanish, and you're left with stuff that has lower depth. I mean, there's a deep connection here between the elliptic story or the modular story and the classical story. I mean, it's not just an artifact, and it can. So between Francis Brown, Makoto Matsumoto, and myself, we gave a completely conceptual proof of this. And, you know, there I stopped again.